Look up at the night sky, and what do you see? Pinpricks of light scattered across an infinite black canvas, each one a distant sun or galaxy, separated by unimaginable gulfs of empty space. But what if I told you that this emptiness is an illusion, that the universe is not a void sprinkled with stars, but a living, breathing structure more intricate and organized than any spider's web? Scientists call it the cosmic web, an immense architecture of invisible filaments that binds the cosmos together, guiding galaxies into clusters and superclusters like beads on an invisible string. This vast network, woven from dark matter and threaded with superheated gas, is one of the most profound discoveries in modern cosmology, and yet it remains one of the least understood. For centuries, we've tried to map the heavens to find order in the chaos, but it's only in recent decades that we've begun to grasp the true complexity of the universe's skeleton. These filaments stretch for hundreds of millions of light years, acting as cosmic highways along which galaxies travel, collide, and evolve. But within these colossal threads lie secrets that defy our current understanding of physics, and enigmas so puzzling they challenge the very foundations of what we know about reality. From inexplicable gravitational anomalies to mysterious energies that seem to flow against the laws of nature, the filaments of the cosmic web are home to phenomena that even our most brilliant minds cannot yet explain. In this video, we're embarking on a journey deep into the heart of this cosmic mystery. Together, we'll explore 25 of the most bewildering and awe-inspiring unexplained phenomena hidden within these filaments, each one a story of discovery, wonder, and the humbling realization of how much we have yet to learn. You'll witness cosmic paradoxes that twist the fabric of space and time, encounter forces that shouldn't exist, and question everything you thought you knew about the universe. This isn't just a tour of strange occurrences, it's an invitation to look beyond the visible, to wonder about the invisible threads that connect us all in this vast, unfolding cosmic story. So let's begin. Our journey into the unexplained begins not with something exotic, but with something profoundly fundamental, the very stuff that makes up you, me, and every star we can see. Cosmologists call this ordinary matter baryonic matter, protons, neutrons, and electrons. Based on meticulous observations of the early universe, specifically the cosmic microwave background, we have a precise recipe for the cosmos. This recipe dictates that this normal matter should account for about 5% of the universe's total mass energy content. The problem: when we add up all the stars, galaxies, and visible gas clouds we can detect, we only find about half of that amount. This is the missing baryon problem, and it represents a colossal accounting error on a universal scale. So where did half the universe's ordinary matter go? The leading suspect for this cosmic hide-and-seek champion is the cosmic web itself. Theorists propose that the missing matter isn't in dense, bright clumps, but is instead spread paper-thin across the vast, invisible filaments of the web. This matter is thought to exist as a searingly hot, diffuse plasma known as the WIM, the warm, hot intergalactic medium. Imagine the hottest steam you can possibly conceive, so tenuous that it contains only a few particles per cubic meter, yet stretched across billions of light years. This gas is simply too hot and too faint to emit light we can easily see, and too diffuse to absorb much light passing through it, making it the ultimate cosmic ghost. Detecting this phantom material is one of the greatest observational challenges in modern astronomy. It's like trying to spot a single, warm breath in a hurricane from 1,000 miles away. Astronomers have had to become detectives, using indirect methods to find their quarry. One technique is to look at the light from incredibly bright, distant objects called quasars. As this light travels through the cosmic web on its billion-year journey to our telescopes, it passes through these filaments. The specific wavelengths of light that get absorbed by the superheated gas act like a fingerprint, revealing the presence and composition of the WIM. Other methods involve looking for subtle distortions in the cosmic microwave background or even hunting for faint flashes of X-ray emission. Yet, even with these ingenious techniques, the ledger still doesn't quite balance. We have found some of the missing matter, but not all of it. This persistent shortfall forces us to ask even deeper questions. Could our understanding of the primordial universe be slightly off? Are there even more exotic forms of this matter lurking in the voids, perhaps in a state we haven't even begun to imagine? The mystery of the missing baryons is a humbling reminder that we are still learning the basic inventory of the cosmos, and that the empty spaces between galaxies are anything but empty. But if finding the universe's missing stuff is a puzzle, the next phenomenon we encounter challenges an even more fundamental rule book, the one that governs gravity itself. Picture a cosmic freeway, a filament of the web spanning hundreds of millions of light years. Galaxies glide along this immense structure, and for the longest time we assumed their motion was a simple, straightforward flow, guided by the gravitational tug-of-war between massive clusters at either end. But recent observations have revealed something far more bizarre and unsettling. Some of these colossal filaments are spinning. They are rotating, much like a giant, impossibly slow whirlpool in the void. This discovery alone would be strange enough, but the real mystery lies in the why. According to our established understanding of physics, a structure of this sheer size and scale simply shouldn't have enough rotational energy to set itself into motion. The initial inertia required to start such an enormous object spinning is almost unimaginable. The prevailing theory points to dark matter as the invisible engine behind this motion. Its gravitational influence, woven throughout the filament, would provide the necessary force to torque and twist this cosmic highway into a slow, deliberate spin. However, when astronomers train their most powerful instruments on these rotating filaments, the evidence they find tells a conflicting story. The observed rotational speeds of the galaxies within these threads are far too high to be explained by the gravitational pull of the visible matter alone. This is a classic signature of dark matter's presence. We see its gravitational effects everywhere else in the universe. Yet, when they search for the telltale signs of that dark matter within the filament itself, through gravitational lensing or the motion of intra-filament gas, the readings come up surprisingly, perplexingly empty. It's as if we're watching a car speed down a highway with no one in the driver's seat and no engine under the hood. This creates a profound cosmological contradiction. The rotation implies dark matter must be there, acting as the hidden driver, but our direct detection methods insist it is not. This forces us to confront several deeply unsettling possibilities. Perhaps our methods for detecting dark matter within these specific environments are flawed, and it is there but hiding in plain sight in a form we cannot yet perceive. Or more radically, perhaps our understanding of gravity itself is incomplete on these vast intergalactic scales. Maybe a modification to the laws of gravitation, something beyond Einstein's relativity, is required to explain how these structures move without a dark matter anchor. This isn't just a missing matter problem, it's a missing force problem. It suggests that the cosmic web is not a passive skeleton but a dynamic, moving structure with mechanics we are only beginning to glimpse. The rotation of these filaments without a clear source of power is a silent revolution in the depths of space, whispering that the rules of the cosmos might be even more complex and wondrous than we ever dreamed. Now let's shift our focus from the motion of the cosmos to its very birth cry. To understand our next great mystery, we must travel back in time, almost to the very beginning of everything. Just 380,000 years after the Big Bang, the universe cooled enough for the first atoms to form, allowing light to travel freely for the first time. That primordial light is still all around us today, bathing the entire universe in a faint, cold glow known as the cosmic microwave background. For cosmologists, this is the most important baby picture in existence, a snapshot of the infant universe. its tiny fluctuations in temperature revealing the seeds that would one day grow into galaxies, clusters, and the vast cosmic web. This background radiation is remarkably uniform, but not perfectly so. It's mottled with slightly warmer and slightly cooler spots like a cosmic fingerprint. Most of these variations are small and perfectly understood, but one spot is different. In the constellation of Eridanus, there exists a colossal cold spot, a region of space where this background radiation is significantly colder than its surroundings. This isn't just a small statistical blip. It's a colossal anomaly, a bruise on the face of the early universe that, according to our standard models, simply shouldn't be there. For a long time, one compelling theory offered an elegant explanation. Perhaps this cold spot wasn't a flaw in the ancient universe, but a trick of the light caused by a much more recent structure. Astronomers proposed the existence of a supervoid, an immense, largely empty region of space lying between us and the cold spot. The theory went that as light from the cosmic microwave background passed through this vast cosmic desert, it would lose a tiny amount of energy as it fought against the gravitational pull of the void. This energy loss, known as the integrated Sachs-Wolf effect, would manifest as a cold spot in our maps. It was a beautiful idea that connected a modern structure to an ancient signal. The hunt for this supervoid was on, and eventually astronomers found one. A massive void indeed aligns with the direction of the cold spot, but here's where the mystery deepens exponentially. This discovered void, as enormous as it is not nearly large enough or empty enough to account for the profound coldness we observe. The numbers simply don't add up. The gravitational drag of this particular void is insufficient to create a cold spot of that magnitude. It's like finding a puddle and trying to blame it for a flood. The void exists, but it cannot be the sole culprit. This leaves us with a chilling dilemma. If the supervoid isn't responsible, then what is? We are forced to consider possibilities that stretch the boundaries of known physics. Some theorists have proposed that the cold spot is evidence of a collision with another universe, a bubble from a vast multiverse brushing against our own in a cosmic fender bender that left a permanent, cooled imprint. Others suggest it could be the signature of an exotic form of energy, a field that interacted with the primordial light in a way we have not yet imagined. The most unsettling possibility of all is that the cold spot is just that, a spot, a statistical fluke of such immense improbability that it exists purely by chance. But the odds of such a fluke occurring naturally in our standard model of the universe are astronomically low, less than 1 in 100. This forces a profound question upon us. Do we accept that we are the winners of a cosmic lottery so unlikely it defies belief? Or do we take it as the strongest hint yet that our understanding of the cosmos is fundamentally incomplete? The cold spot stands as a silent, freezing sentinel, guarding the secrets of either a statistical miracle or a doorway to physics beyond our wildest dreams. Moving from the grand, mysterious motions of the cosmos, we now turn our gaze to the inhabitants of these great cosmic highways. Galaxies are the cities of the universe, and like cities on Earth, they come in all shapes and sizes, spiraling metropolises, dense elliptical hubs, and small, dwarf town satellites. But drifting within the filaments of the cosmic web, astronomers have discovered a class of galaxies so strange, so counterintuitive, that they seem to defy the very logic of how galaxies are built. These are the ultra-diffuse galaxies, and they are the cosmic equivalent of ghosts. Imagine a galaxy the size of our own Milky Way, a sprawling disk spanning 100,000 light-years. Now imagine that instead of containing hundreds of billions of brilliant stars, this vast expanse holds less than 1% of that number. The result is an object of profound paradox, a galaxy that is incredibly large yet almost transparent. Its few stars are so widely spaced that you could travel from one solar system to the next and see nothing but blackness for thousands of light years. If you were inside one, the night sky would be nearly empty, a desolate and starless void. From the outside, these galaxies are so faint they were only discovered when our telescopes became powerful enough to see these faint smudges against the blackness of space. Their mere existence is a puzzle, but their location makes the mystery even deeper. These ghostly galaxies aren't found in the isolated boondocks of the cosmic web. They are residents of the filaments themselves, the bustling interstates that connect massive clusters. This is a high-density environment, a place where gravitational tides and interactions between galaxies are common. According to our established theories of galaxy formation, such a fragile, wispy structure should have been torn apart eons ago by the gravitational forces of its larger, denser neighbors. The fact that they have survived this cosmic gauntlet suggests they are far tougher than they appear. This is where the plot thickens into a full-blown cosmological thriller. When astronomers study the motion of the scant stars within these ultra-diffuse galaxies, they uncover an astonishing secret. The stars are moving far too quickly for the amount of visible mass present. The only explanation is that these seemingly empty, fragile galaxies are, in fact, anchored by absolutely enormous halos of dark matter. In some cases, these galaxies may contain as much dark matter as the Milky Way, but with almost none of the stars. It's as if we found a skyscraper that was all foundation and hidden support structures, with only a single, dimly lit room at the very top. This revelation turns galaxy formation theory on its head. We thought we understood the basic recipe. A halo of dark matter forms first. Its gravity then pulls in ordinary gas, which cools, condenses, and eventually forms stars. The ratio of dark matter to visible matter was thought to be somewhat consistent, but ultra-diffuse galaxies break this mold entirely. They have the dark matter scaffolding of a massive galaxy, but failed spectacularly at the star making part of the process. Why? Did their gas get stripped away by interactions with other galaxies in the filament before it could form stars? Were their internal conditions somehow unsuitable, perhaps too stable or not dense enough to trigger star formation? Or does their dark matter have a different, more inert property that prevents it from efficiently gathering gas? These ghostly galaxies force us to reconsider the diversity of galactic life. They are living fossils, preserving a record of a failed or stalled evolutionary path. Their resilience within the violent environments of filaments, bolstered by their unseen dark matter armor, suggests that the cosmic web is not just a structure for guiding galaxies, but also a museum displaying the bizarre and unexpected outcomes of cosmic evolution. They are a silent testament to the fact that for all the rules we think we've written about the universe, it always has a way of showing us something entirely new. And if the ghostly ultra-diffuse galaxies challenge our understanding of how matter assembles, the next phenomenon we encounter questions the very principle upon which all of modern cosmology is built. For centuries, a fundamental assumption has guided our study of the universe, the cosmological principle. This is the idea that on a sufficiently large scale, the universe is homogeneous and isotropic. In simpler terms, it means that no matter where you are in the cosmos, if you zoom out far enough, the universe should look roughly the same in every direction, a uniform, cosmic soup of matter and energy. It's a comforting, democratic idea that suggests there is no special place in the universe. But what if we found one? In 2013, while mapping the locations of gamma-ray bursts, the most powerful explosions in the universe, thought to mark the deaths of massive stars, astronomers stumbled upon something that shouldn't exist. They noticed a startling concentration of these bursts in the constellations of Hercules and Corona Borealis, a region of space that suggested an unimaginably vast congregation of galaxies. Further analysis revealed this was not just a cluster or a supercluster. It was a structure of almost inconceivable proportions. They named it the Hercules Corona Borealis Great Wall, and it is so enormous that it threatens to tear a hole in our standard model of the cosmos. To grasp its scale, consider that our entire Milky Way galaxy is roughly 100,000 light-years across. The distance from our galaxy to our nearest large neighbor, Andromeda, is 2.5 million light-years. The Hercules Corona Borealis Great Wall spans an astounding 10 billion light-years. That is over a tenth of the diameter of the entire observable universe. This isn't just a structure, it is a continent of galaxies, a cosmic empire so vast that its sheer existence seems to mock the idea of universal homogeneity. Finding a structure this big is like stirring a pot of vegetable soup and finding a single, continuous carrot that stretches from one side of the pot to the other. The problem is one of timing and physics. According to the Big Bang model, the universe is 13.8 billion years old. The principle of homogeneity is expected to hold on scales larger than about 1.2 billion light-years, as this represents the maximum distance over which information or causal contact could have traveled since the beginning of time to smooth things out. The Great Wall is nearly 10 times larger than this theoretical limit. This means there is no physical way that this structure could have formed through the known forces of gravity and cosmic evolution. It simply wouldn't have had enough time to assemble itself into such a coherent, gigantic form. It is a structure that, by all rights, is cosmologically impossible. This leaves scientists grappling with a series of deeply unsettling questions. Could our understanding of the very early universe, of inflation and the initial conditions of the Big Bang be fundamentally flawed? Perhaps the universe is not as uniform as we thought, and we must revise the cosmological principle itself, accepting that we do, in fact, live in a special place next to one of the universe's grandest features. Or perhaps the fault lies not in our models but in our interpretation of the data. Some researchers have proposed that the Great Wall might be a statistical illusion, a trick of perspective where multiple smaller, unrelated structures along our line of sight appear connected, creating a phantom continent in the sky. Yet, with each subsequent survey and map, the evidence for this colossal formation only grows stronger. It stands as a stark, monumental challenge to our comprehension of the cosmos. A reminder that the universe has a habit of presenting us with wonders that defy our most cherished principles. The Hercules Corona Borealis Great Wall is more than a collection of galaxies. It is a question written across 10 billion light-years, asking us if we truly understand the fabric of reality, or if we are only just beginning to read its first bewildering words. These colossal, mysterious structures bring us to our next great enigma, one that isn't seen in visible light but heard in the deep, rhythmic hum of the radio universe. Imagine once more the vast, dark filaments of the cosmic web. Now picture within them not just galaxies and hot gas, but titanic, symmetrical bubbles. These aren't mere pockets of empty space. They are immense spheres of radio wave emission, some spanning millions of light-years, floating within the filamentary highways like soap bubbles caught in a spider's web. Astronomers call them cosmic radio bubbles, and their discovery was as accidental as it was baffling. These bubbles were first detected not by optical telescopes, but by massive radio antenna arrays that listen to the universe's longest wavelength. The signals revealed perfectly defined, often paired, spherical regions within filaments, glowing fiercely with synchrotron radiation. This is a very specific type of emission that only occurs when electrons are accelerated to nearly the speed of light and then forced to spiral around powerful magnetic field lines. It's the signature of a tremendous, violent release of energy. The immediate, pressing question is this: what immense engine, what cosmic event could possibly punch such enormous, energetic cavities into the fabric of a filament? The most logical suspect is an active galactic nucleus, or AN. This is the supermassive black hole at the heart of a galaxy gone rogue. When such a black hole is actively feeding on surrounding gas and dust, it doesn't just swallow matter, it can become the most powerful engine in the universe. It converts gravitational energy into intense radiation and, crucially, it can launch two opposing jets of magnetized, ultra-relativistic particles that scream across space at nearly the speed of light. It's thought that these jets can plow into the surrounding intergalactic medium within a filament, inflating gigantic bubbles of hot, radio-emitting plasma on either side of the galaxy. We see this happen on smaller scales within galaxy clusters, where AGNs are known to blow bubbles into the cluster's gas. But when we look at these specific radio bubbles nestled within the filaments themselves, the AGN explanation starts to develop serious holes. The sheer scale of some of these bubbles is staggering, far larger than what a typical supermassive black hole should be capable of producing. More critically, in many cases, astronomers have pointed their telescopes directly at the center of these bubble pairs, expecting to find the glaring, unmistakable beacon of a hyperactive black hole, the presumed culprit. Yet, all too often, they find nothing. There is no galaxy there powerful enough, no active galactic nucleus bright enough to have been the architect of such colossal structures. It's as if we found a perfectly carved tunnel through a mountain, but no evidence of the dynamite, the machinery, or the workers that could have created it. This void of evidence forces us to consider sources of energy that are far more exotic and perhaps even invisible. One compelling, though speculative, theory points its finger at the universe's greatest mystery itself, dark matter. What if, deep within these filaments, concentrations of dark matter particles are colliding and annihilating each other, or slowly decaying into known particles? Such a process would release an incredible flood of energy, along with the very same high-energy electrons that produce the synchrotron radiation we detect. The filament, dense with both normal gas and dark matter, would provide the perfect fuel for this reaction, and the resulting explosion of energy could inflate the radio bubbles we observe. This would mean these bubbles are not the result of a single galactic event, but a direct signal from the dark sector itself, a visible testament to the hidden physics of the universe's dominant but unseen component. Alternatively, these bubbles could be the ancient, fading fossils of events that occurred in the deep past. Perhaps a supermassive black hole was indeed active there billions of years ago, but has since consumed all its fuel and fallen silent, its brilliant jets shutting off and leaving its enormous, expanding bubbles to slowly fade away over eons. Or perhaps we are witnessing the cumulative effect of many smaller, stellar explosions supernova, from an entire population of stars that formed within the filament itself, their combined winds and shocks creating a vast, unified structure. Whatever their origin, these cosmic radio bubbles represent a profound transfer of energy into the cosmic web. They are agitators stirring the pot of the intergalactic medium, heating the gas within the filaments and potentially affecting how and where future galaxies can form. They remind us that these filaments are not static backdrops. They are dynamic environments shaped by violent and energetic events that we are only beginning to catalogue. Their silent radio wave hum is a message from the depths of space, a message we are still struggling to decode, about forces that can shape the universe on a scale we can barely comprehend. This brings us to a mystery that hits far closer to home, one that suggests our very place in the cosmos might not be as ordinary as we once believed. We return once more to that ancient baby picture of the universe, the cosmic microwave background. As we said, its tiny temperature fluctuations are meant to be random, the chaotic fingerprints of quantum noise from the universe's first moments stretched across the sky by inflation. They should form a random, unpredictable pattern, a celestial snowstorm with no order or design. But when scientists began to analyze this map with ever-increasing precision, they noticed something that sent a chill through the field of cosmology. The fluctuations weren't completely random. Some of the largest and most significant patterns seemed to be mysteriously aligned with each other. And even more bizarrely, they appeared to be oriented in a way that relates to our own solar system. This perplexing and to some deeply troubling discovery has been dramatically dubbed the axis of evil. The name itself reflects the level of discomfort this finding causes. In the standard cosmological model, there should be no special direction in the universe and certainly no axis that somehow correlates with our local neighborhood. That would be a shocking violation of the Copernican principle, the idea that we do not occupy a privileged position in the cosmos. The axis refers to a particular alignment of the larger fluctuations, almost as if they are arranged on a great circle in the sky. The evil part comes from the profound philosophical problem it creates. If this alignment is real and not a mistake, it implies that we are, in fact, at the center of something, a notion modern science had supposedly left behind centuries ago. The most startling aspect of this alignment is its connection to our own ecliptic plane, the flat disk traced by Earth's orbit around the Sun. The plane of our solar system seems to define this preferred direction in the universe's oldest light. This is utterly inexplicable. Why would the structure of the entire observable universe, set in stone when it was just a newborn, bear any relation to the orientation of a tiny planetary system that wouldn't form for another 9 billion years? The connection is so absurd that the immediate and entirely reasonable assumption was that it must be a terrible error. Perhaps it's a systematic contamination in the data, an artifact introduced by our own instruments or by the way we subtract the foreground glow of our own galaxy. Yet, despite over 2 decades of intense scrutiny and the launch of increasingly sophisticated satellites like Planck designed specifically to root out such errors, the anomaly persists. It refuses to be washed away by better data. With each new, more precise map of the cosmic microwave background, the alignment signal, while not getting stronger, stubbornly remains at a low but statistically significant level. It's a ghost in the data that we cannot exorcise. This forces the scientific community to confront 2 equally unpalatable possibilities. The first is that there is a subtle, unknown systematic error that has somehow fooled the world's top cosmologists and their multi-billion-dollar satellites for a generation. The second, far more radical option is that the alignment is real and our fundamental understanding of the universe is wrong. If we dare to entertain the latter notion, the implications are staggering. It could mean that the vast universe is not isotropic and homogeneous on the largest scales as we have believed, but has some form of large-scale structure or directionality that we are only just glimpsing. Perhaps the Big Bang itself was not perfectly symmetric, imparting a kind of spin or preferred direction to the fabric of spacetime that is imprinted on the cosmic microwave background. Some speculative theories even suggest this could be a hint of something beyond our universe, a gravitational tug from a neighboring universe in the multiverse, or evidence that our cosmos is rotating as a whole, an idea that would require a complete overhaul of Einstein's equations. The axis of evil remains one of the most controversial and philosophically charged puzzles in modern cosmology. It is a whisper from the void that suggests either our instruments are deeply flawed or our place in the cosmos is strangely special. It's a reminder that for all our grand theories and maps of the cosmic web, the universe may still be keeping its deepest secrets, secrets that challenge not just our models, but our very understanding of reality and our place within it. Just when we thought the cosmic mysteries couldn't get any more profound, we encounter a phenomenon that challenges not just what exists in the universe, but how the entire cosmos is moving as a whole. This brings us to one of the most disconcerting enigmas in modern cosmology, the mystery of dark flow. Imagine you're standing in a vast, open field during a gentle snowfall. The snowflakes appear to be falling straight down, a serene and uniform motion, but then you notice something strange. All the snowflakes, every single one, are also drifting ever so slightly in the same specific direction, as if pulled by a silent, unseen wind. Now scale that image up to a cosmic level. Galaxies and their clusters are like those snowflakes, and according to our best models, their motions should be governed by the gravitational tug of nearby matter, the pull of massive superclusters and the great walls of the cosmic web. Their movements should be local and random, a chaotic dance dictated by their immediate surroundings. However, that is not what astronomers observed. Using the incredibly precise data from the Wilkinson Microwave Anisotropy Probe satellite, scientists tracked the motion of enormous galaxy clusters by studying a subtle effect on the cosmic microwave background. As these massive clusters move through space, their hot gas scatters the photons of the ancient background light, creating a very faint but detectable temperature shift that reveals both their speed and direction. When they compiled this data from over 1,000 clusters, they expected to see a random scatter of motions. Instead, they found a coordinated stream. A vast collection of clusters stretching across billions of light years was all moving in the same direction at a breathtaking speed of over 600 miles per second. This isn't a local flow, it's a bulk flow, a cosmic river on the grandest possible scale, and its existence defies all conventional explanation. The gravitational influence of every single known structure in the observable universe, every galaxy, every cluster, every filament of the cosmic web we've ever mapped, is utterly incapable of causing this coordinated motion. It would require a gravitational pull from something so immense, so unimaginably massive, that its tug is felt across nearly a tenth of the entire observable universe. But when we look in the direction of this flow, we see nothing. There is no known concentration of matter, no supercluster, no great wall large enough to account for this motion. The only thing there is a more universe. This is why it was christened dark flow, because its cause is completely invisible and unknown, much like dark matter and dark energy, but perhaps even more strange. This discovery forces us to consider possibilities that lie at the very edge, and perhaps beyond, of theoretical physics. The most startling hypothesis is that the gravitational source for the dark flow lies outside our observable universe. Think about what that means for a moment. The observable universe is the spherical volume of space from which light has had time to reach us since the Big Bang. It is our cosmic horizon. The idea that something beyond that horizon, something we can never see, could be exerting a gravitational influence on us is both revolutionary and deeply unsettling. It suggests that the structure of the cosmos extends far beyond what we can observe, and that whatever lies out there is not uniform. It implies a cosmic imbalance on a scale we can scarcely conceive, a gravitational gradient so steep that it can pull on thousands of galaxies from beyond the veil of space-time. Other theories are no less extraordinary. Could this flow be a remnant of the inflationary epoch, a kind of cosmic drift imprinted on the fabric of the universe in its first fleeting moments? Or does it point to a collision with another universe in the multiverse, a titanic event that set our entire cosmic domain moving in a specific direction? The very fact that such speculative ideas are being seriously discussed highlights how profound a puzzle the dark flow presents. It's a reminder that our map of the cosmos is still incomplete, and that the greatest structures or the most powerful forces may still be lurking in the shadows just beyond our sight, guiding the motion of the heavens in ways we are only beginning to sense. Yet, even as we grapple with these immense flows and alignments, we must also confront a mystery that lies in the tiniest of details, one that emerges from the very first minutes of creation. To understand it, we rewind the clock all the way back to when the universe was just a few minutes old. In this furious, newborn state, the entire cosmos was a searing hot nuclear fusion reactor. Protons and neutrons slammed together, forging the first atomic nuclei in a process we call Big Bang nucleosynthesis. This brief, explosive period created almost all the hydrogen and helium in the universe today, along with trace amounts of two other light elements, deuterium, a heavy form of hydrogen, and lithium. The precise amounts of these elements produced are a fundamental prediction of the standard cosmological model, a direct consequence of the universe's density and expansion rate in those first moments. For the most part, this prediction is a stunning success. When we look at the oldest, most pristine gas clouds in the universe, often found in the diffuse regions of cosmic filaments, far from the polluting influence of later generations of stars, the observed abundances of hydrogen, helium, and deuterium match the theoretical predictions with breathtaking accuracy. It is one of the cornerstone validations of the Big Bang theory, but there is one glaring, persistent exception: lithium. The models predict that there should be about 3 times more lithium-7, the most common isotope, in these ancient gas clouds than what we actually observe. This discrepancy is not a small margin of error. It is a factor of 3, a colossal mismatch known simply as the lithium problem. This isn't just a minor accounting error. It's a fundamental crack in the foundation of our understanding of the universe's first 3 minutes. Lithium is a fragile element. It can be easily destroyed in the hot interiors of stars. So, for decades, the leading theory was that the lithium we see in old stars had simply been burned away over time. The solution, it seemed, was to look for the primordial lithium signature in the most pristine places of all, the gas within the cosmic filaments. This gas has never been processed through a star. It is the pure, unaltered residue of the Big Bang itself. But when astronomers finally developed the techniques to measure the lithium abundance in this filament gas, the problem didn't go away. The number was still 3 times lower than predicted. The lithium was missing from the very beginning. This forces us to confront a series of deeply intriguing possibilities, each one more radical than the last. The first is that our understanding of nuclear physics during that initial 3-minute period might be incomplete. Perhaps there is an unknown nuclear reaction pathway that destroyed lithium as it was being formed, a resonance or a decay process that our current models of particle physics do not account for. Researchers have scoured the possibilities, but so far, no conventional solution has been found. Another avenue points to exotic physics. Could dark matter have played a role in the early universe's chemistry? Certain types of hypothetical dark matter particles, if they existed, could have interacted with the primordial soup of nuclei and altered the outcome of Big Bang nucleosynthesis, specifically by depleting lithium. This would mean that the fingerprint of dark matter is not just in the gravity of galaxies, but etched into the very atomic composition of the universe. A third, and perhaps most mind-bending, possibility is that the lithium problem is a clue that the universe was not as uniform in its first moments as we believe. Our predictions assume a perfectly smooth, homogeneous soup of particles, but what if there were tiny variations in density or temperature on those minuscule scales? These fluctuations could have created pockets where nuclear burning proceeded slightly differently, leading to an overall lower yield of lithium than our models, which average everything out, would predict. The lithium problem is a quiet but persistent alarm bell ringing from the dawn of time. It tells us that even in our greatest successes, there may be hidden failures. That a theory which so perfectly predicts the amounts of hydrogen, helium, and deuterium could be so confidently wrong about lithium suggests that a piece of the puzzle is still missing. It is a reminder that the universe's first few minutes might hold secrets about fundamental physics that we can only uncover by reading the faint, ancient signature of a missing element in the vast, dark threads of the cosmic web. Now, let's shift our focus from the grand ballet of moving galaxies to a far more subtle, yet equally mysterious, force that seems to be woven into the very fabric of the cosmic web itself: magnetism. We are all familiar with magnetic fields on Earth. They guide our compasses, hold notes on our refrigerators, and are generated by the churning of molten metal in our planet's core. We also know that magnetic fields exist throughout the cosmos, from the powerful fields around neutron stars to the more modest ones that spiral through galaxies like our own Milky Way. But what about the space between the galaxies, the immense dark voids within the cosmic filaments? For a long time, it was assumed these vast regions were true voids in every sense, empty not only of visible matter but also of large-scale magnetic influence. That assumption has been completely overturned. Astronomers, using incredibly sensitive radio telescopes, have begun to detect the faint but unmistakable signature of organized magnetic fields stretching along the lengths of these cosmic filaments. This discovery is as puzzling as it is profound. We understand how a planet or a star generates a magnetic field through the motion of conductive material like liquid iron, a process called a dynamo. We even have theories for how galaxies can amplify and maintain their fields over time. But a filament, these are structures millions of light years long, composed of incredibly diffuse gas with a density of perhaps 1 atom per cubic meter. It's a near-perfect vacuum, an environment seemingly devoid of the internal motions or energy sources needed to create, let alone sustain, a coherent magnetic field across such an unimaginable scale. It's like discovering a persistent, powerful magnetic field stretching across an entire ocean, but finding no source for it, no hidden generator, no flowing currents, nothing but the water itself. The immediate question is one of origin. Where did these fields come from? One leading theory suggests they are primordial, a relic from the universe's very infancy. In the first fractions of a second after the Big Bang, during a period of rapid expansion known as inflation, quantum fluctuations could have been stretched to cosmic sizes, seeding space itself with tiny magnetic fields. These weak seed fields would then have been amplified and woven into the cosmic web as structure formed, carried along by the flows of gas and dark matter that built the filaments. It's an elegant idea, suggesting that magnetism is a fundamental property of space-time, as intrinsic as gravity. However, the primordial theory faces its own set of challenges. The process of amplifying these weak seed fields to the strengths we observe is not well understood. Furthermore, the fields we detect appear to be surprisingly organized, often aligned with the filament structure. This degree of coherence over billions of years is difficult to explain if they are just passive relics being stretched and pulled by gravity. They seem too well ordered, too maintained. This leads to a second, more dynamic possibility, that the fields are generated in situ within the filaments themselves. But what could possibly power such a cosmic-scale dynamo? The turbulent motion of gas as it flows along the filament into giant galaxy clusters could generate some magnetic activity, but it's unclear if this is sufficient. Another provocative idea implicates the cosmic rays and high-energy particles that are constantly being shot out from supernova and active black holes within the filament's galaxies. As these particles travel, they could create currents that generate magnetic fields, effectively turning the entire filament into a faint, sprawling electrical circuit. This would mean the magnetic field is not a relic of the past, but a living, dynamic phenomenon, continuously energized by the violent events happening within its domain. Yet, when we go looking for these proposed energy sources, we often come up short. The predicted turbulence isn't always observed, and the energy output from the galaxies within a filament doesn't always seem adequate to power a magnetic field of that scale and coherence. This brings us back to a now familiar character in our cosmic mystery, dark matter. Could certain theoretical types of dark matter particles, perhaps those that interact with each other through a dark force, generate these fields? Or could the decay of dark matter be providing a faint, ubiquitous energy source that helps sustain magnetism in the void? It's a highly speculative idea, but it underscores how these magnetic fields force us to consider physics beyond the standard model. The presence of these mysterious fields is far from an academic curiosity. They have a real and tangible effect on the evolution of the cosmos. Magnetic fields can influence the collapse of gas clouds to form new galaxies. They can guide the paths of high-energy cosmic rays, and they can affect how heat is distributed throughout the intergalactic medium. They are an invisible hand, subtly shaping the story of cosmic structure. Their unexplained origin and persistence remind us that even the apparent emptiness of space is filled with hidden forces and intricate physics, a silent, magnetic symphony playing out in the darkest reaches of the cosmic web. But just as we find ourselves peering into the primordial past to solve the lithium problem, another, more contemporary crisis is unfolding in our measurement of the present-day universe, and it too finds a strange amplification within the intricate structure of the cosmic web. This is the Hubble tension, a stubborn and growing discrepancy that strikes at the very heart of modern cosmology. The Hubble constant, known as H0, is arguably the most important number in cosmology. It tells us the current rate of expansion of the universe, how fast galaxies are receding from us as the very fabric of spacetime itself stretches. For decades, astronomers have worked to pin down this number with ever greater precision, expecting that different methods would eventually converge on a single, universal value. Instead, they have diverged, creating a chasm of disagreement that the cosmic web seems to deepen. On one side of this divide, we have the meticulous measurements of the early universe. By studying the detailed fluctuations in the cosmic microwave background, that same ancient light that revealed the axis of evil scientists can extrapolate forward through 13.8 billion years of cosmic evolution using our well-tested standard model of cosmology, lambda cold dark matter. This method provides a very precise prediction for what the Hubble constant should be today. On the other side, we have direct measurements of the local, modern universe. Astronomers use what are called standard candles, objects like Cepheid variable stars and Type Ia supernova, whose intrinsic brightness is known. By measuring how bright they appear from Earth, we can calculate their distance, and by measuring their redshift, we can see how fast they are moving away. This gives us a direct, empirical value for the expansion rate right now. The problem is stark. The early universe method and the late universe method do not agree. Their results are separated by a gap that has now grown to a level of over 5 sigma, meaning there is less than a 1 in a million chance that this is a random fluke. The universe's own 2 clocks are ticking at different rates. This is where the cosmic web enters the story, not as a solution, but as a mysterious amplifier of the problem. One would hope that by using the web structure itself as a measuring stick, we could find a resolution. The vast ruler-straight filaments provide a natural standard ruler. By studying how these structures appear at different redshifts, we can independently measure the expansion history of the universe. Other techniques involve using the gravitational lensing of light as it passes through these massive filaments, or timing the delays between multiple images of a quasar created by a filament's gravity. These are powerful, sophisticated methods that operate on the grandest scales, yet when the results come in, they don't neatly side with one camp or the other. Instead, they often land in a perplexing no-man's land, sometimes leaning towards the early universe value, sometimes towards the late universe value, but rarely providing a definitive answer. It's as if the cosmic web itself is refusing to take a side, adding its own layer of ambiguity to the debate. This inconsistency within the web's measurements is in many ways more troubling than the original tension. It suggests that the problem may not be a simple error in one method, but something far more fundamental. Perhaps our understanding of gravity within these vast filamentary structures is incomplete. The standard model assumes gravity works exactly as Einstein predicted, even across these immense scales of mostly empty space. But what if it doesn't? What if the presence of these vast, dark matter-dominated filaments modifies the gravitational field in a way we haven't accounted for, subtly skewing our distance measurements? Or perhaps the issue is with the dark energy that permeates the voids between the filaments. Our model assumes it is a constant force, but if its strength has varied over time, or if it interacts differently with the dense environments of filaments versus the empty voids, it could create the conflicting results we observe. The most exciting possibility is that the Hubble tension, as revealed through the lens of the cosmic web, is our first direct evidence for new physics beyond the standard model of cosmology. It could be a hint that dark energy is dynamic, or that dark matter possesses some unknown property, or even that there are additional types of neutrino-like particles that influence the expansion history. The cosmic web, acting as a colossal particle accelerator and gravitational lens all in one, is where these subtle effects would be most pronounced. The fact that its measurements deepen the mystery rather than resolve it is a powerful clue that we are on the verge of a monumental discovery. The Hubble tension is no longer just a debate about a number. It is a profound question about the laws of physics themselves, and the cosmic web is the arena where this cosmic drama is playing out. This journey into the cosmic web continually reveals that our expectations are built upon a foundation of sand, and nowhere is this more thermally apparent than in the very temperature of these vast structures. We've long imagined the filaments as relatively cool rivers of gas, passively channeling material into the waiting gravitational wells of galaxy clusters. The logic was straightforward. As gas flows into these filaments from the emptier voids, it should compress and shock, heating up somewhat, but then gradually cool over time through the emission of radiation. Our models predicted filaments should be warm, perhaps a few 100,000 degrees, but recent observations have scorched that assumption to ashes. Astronomers using space-based X-ray telescopes have been stunned to find filaments that are searingly, inexplicably hot, reaching temperatures of tens of millions of degrees, a heat rivaling the very cores of galaxy clusters themselves. This is the thermodynamic equivalent of finding a river of molten lava where a cool mountain stream was supposed to be. Such intense heat cannot be sustained by the passive process of gravitational infall alone. It demands a powerful, continuous, and unidentified heating source. A filament is not a star. It has no internal nuclear furnace. So what colossal cosmic engine is pumping energy into this diffuse gas, keeping it at a rolling boil across millions of light years? The immediate suspects are the usual galactic troublemakers, active supermassive black holes and bursts of supernova explosions from within the galaxies that call the filament home. These entities are known to flood their surroundings with high-energy particles and powerful winds, and it seemed logical that they could be responsible for turning up the thermostat. Yet, upon closer inspection, this explanation begins to evaporate. In many of these superheated filaments, there simply aren't enough active galaxies or recent supernova to account for the phenomenal and sustained energy input required. The math falls woefully short. It would be like trying to heat an entire ocean with a single candle. This forces astronomers to consider far more exotic and pervasive heating mechanisms. One compelling theory points to the filament itself acting as a colossal particle accelerator. The vast magnetic fields we just discussed could be trapping high-energy cosmic rays, protons, and atomic nuclei accelerated to near light speed by black holes and exploding stars. These trapped particles would continuously buffet the filament's gas, transferring their immense kinetic energy as heat in a process called cosmic ray heating, effectively turning the entire structure into a slow cooker. Another provocative idea delves into the realm of dark matter. If certain types of dark matter particles are not completely stable but can decay or annihilate upon collision, they would release a steady drizzle of energy into the normal matter of the filament. This would provide a ubiquitous, invisible heat source woven directly into the fabric of the cosmic web, a background radiation of destruction that we cannot see but can feel in the form of this unexpected warmth. This would mean the temperature of a filament is not just a record of recent stellar violence, but a direct thermometer into the properties of the universe's most mysterious substance. The implications of these unexplained temperatures ripple outward, affecting everything we know about how galaxies form and evolve. Gas must cool to condense and collapse into new stars. If the raw material for galaxy formation is perpetually being superheated within the very highways that feed clusters, it could dramatically slow down or even halt star formation in certain regions. These filaments may not just be conduits of matter, but active regulators of galactic growth, their mysterious heat acting as a cosmic hand on the thermostat, controlling the birth rate of stars across the universe. This unsolved thermal mystery reminds us that the cosmic web is a dynamic and energetic system, and that the empty spaces between the galaxies are crackling with a power we are only beginning to sense. For decades, astronomers mapping the grand motions of galaxies in our cosmic neighborhood noticed something deeply peculiar. On top of the general expansion of the universe, which sees all galaxies receding from each other, our entire local group of galaxies, including the Milky Way and Andromeda, is moving with a tremendous velocity in a specific direction. This isn't a random drift, it's a coordinated flow, as if our entire region of space is caught in a powerful, unseen current. When scientists traced this current backwards, they found it was part of a much larger river of galaxies, thousands of them, all streaming toward a single point in the depths of space. This invisible center of gravitational influence was named the Great Attractor, and its location presented an immediate and frustrating problem. It lies directly behind the plane of our own Milky Way galaxy, in a region astronomers call the zone of avoidance. Our galaxy's disk is thick with gas, dust, and countless stars, creating a brilliant, obscuring band across the sky that completely blocks our optical view of what lies beyond. It's like trying to see a distant mountain range through a dense, perpetual fog. For a long time, the Great Attractor was a ghost, its immense gravitational pull felt but its true identity completely hidden from sight. Early estimates suggested it was a massive concentration of matter, perhaps a supercluster of unprecedented size, with a gravitational pull equivalent to tens of thousands of Milky Ways. But the nature of this colossal hidden structure remained one of the sky's most compelling secrets. The breakthrough began with new eyes on the cosmos. We developed telescopes that could see the universe in wavelengths of light that pierced through the galactic fog. Infrared surveys and radio telescopes, particularly those mapping hydrogen gas, started to peel back the layers of the zone of avoidance. What they revealed was astonishing, yet it only deepened the mystery. There was indeed an immense concentration of mass there, a gigantic supercluster now known as the Norma Cluster, located about 220 million light-years away. This discovery was a major step forward, but it immediately created a new paradox. While the Norma Cluster is undeniably massive, its gravitational strength is still not nearly powerful enough to account for the observed velocity of our motion. It's as if we felt the pull of a planet, only to finally break through the clouds and find a large moon. The numbers simply don't add up. The bulk of the attractor's force was still missing. This realization propelled the mystery to an even grander scale. If the Norma supercluster is merely a waypoint, then what is the true source of the pull? The river of galaxies, it turns out, does not stop at the Great Attractor. It flows through it. Our motion, and the motion of thousands of other galaxies, is part of a far vaster flow toward an even more immense and distant structure. This ultimate destination is now known as the Shapley Attractor, the largest concentration of matter in our observable universe, a staggering supercluster located over 600 million light-years away. Its gravitational influence is truly titanic, and it seems to be the primary engine behind the bulk flow we experience. But here lies the modern incarnation of the Great Attractor anomaly. Even with the immense mass of the Shapley supercluster included in the calculations, a troubling discrepancy remains. The observed velocity of our motion is still slightly higher than what the combined gravitational pull of Shapley, the Norma supercluster, and all other known structures in that direction can explain. There is still a missing source of gravity, a hidden component to the attractor that continues to elude us. This has led scientists to propose some extraordinary explanations. Could there be even more mass hidden behind Shapley itself that we cannot yet see? Or does this persistent discrepancy hint at something more fundamental? Perhaps our understanding of gravity itself behaves differently on these immense inter-supercluster scales. Maybe the laws that govern the pull between planets and stars need refinement when applied to the vast filamentary architecture of the cosmic web. The great attractor anomaly has evolved from a quest to find a single hidden object into a profound lesson about the interconnected nature of the universe. It taught us that galaxies do not move in isolation but are carried along by immense cosmic currents, driven by the gravitational tides of the largest structures in existence. The mystery is no longer about a single point in space, but about understanding the complete gravitational landscape of our cosmic neighborhood and reconciling it with the subtle, unexplained motions we feel. It stands as a powerful reminder that even as we map the cosmos, the deepest sources of its motion may still lie just beyond the edge of our vision, pulling us toward discoveries we have not yet imagined. This brings us to a concept so bizarre it seems ripped from the pages of science fiction, yet it may be woven into the largest structures in existence. We are venturing into the quantum realm, but not on the tiny scale of particles. We are talking about quantum entanglement operating across millions of light years within the very filaments of the cosmic web. In the laboratory, quantum entanglement is a well-documented, if deeply strange, phenomenon. It occurs when two particles become inextricably linked, their fates intertwined so that measuring the property of one particle instantly determines the property of the other, no matter how far apart they are separated. This spooky action at a distance, as Einstein famously called it, defies our classical intuition about how information can travel. For decades, this was considered a peculiarity of the microscopic world, an effect that would be far too fragile to survive in the noisy, hot environment of the cosmos. The idea that such a delicate quantum connection could persist on a cosmic scale seems, at first glance, utterly preposterous. The cosmic web is a realm of immense distances, intense radiation, and violent interactions, conditions that should instantly shred any fragile quantum linkage. Yet, a small but growing number of theoretical physicists are proposing that the universe's largest structures might be held together by more than just gravity. They suggest that the quantum entanglement that was forged in the ultra-dense, ultra-connected first moments of the Big Bang might not have completely severed. Instead, as the universe expanded, these primordial quantum connections could have been stretched to astronomical sizes, imprinting themselves onto the distribution of dark matter and gas that would eventually form the cosmic web. In this radical view, the filaments are not just gravitational structures, they are also quantum structures, their very existence a testament to a connectivity that transcends space and time. The evidence for this is, of course, indirect and highly controversial, but it is beginning to emerge from sophisticated computer simulations of the universe's evolution. When cosmologists run models that try to replicate the precise pattern of the cosmic web we see today, the exact distribution of clusters, filaments, and voids, they sometimes find that the models only match reality if they include a certain level of unexpected correlation between distant, seemingly disconnected regions of space. It's as if the model is telling them that things which have never been in causal contact still somehow know about each other. This is exactly the kind of long-range connection that quantum entanglement could provide. It would be a hidden network of information, a subtext of quantum communication running through the universe's skeletal structure. The most tantalizing and debated potential observations come from studying the cosmic microwave background. Some researchers claim to have detected strange, non-local correlations in the patterns of hot and cold spots on this ancient map, correlations that cannot be explained by any known physical process that operated after the Big Bang. These patterns, they argue, could be the fossilized imprint of quantum entanglement between patches of the early universe that were once in close contact but were then flung far apart by inflation. If true, this would mean that the largest patterns we see in the sky today were literally written by quantum connections in the first trillionth of a second of existence. Skepticism remains the default position, and rightly so. The leap from lab-scale experiments to cosmic-scale phenomena is monumental. Critics argue that the observed correlations could be statistical flukes, or that there may be more conventional, if undiscovered, physical processes that can explain them. The very idea challenges the principle of locality, a cornerstone of physics which states that an object is only directly influenced by its immediate surroundings. Cosmic quantum entanglement would mean that the universe is fundamentally non-local, that particles in one galaxy could be instantaneously influencing particles in another galaxy a billion light-years away, a notion that still makes most physicists deeply uncomfortable. Yet the possibility is too profound to ignore. If validated, it would represent a unification of physics on the grandest possible scale, weaving together the quantum world with the cosmos. It would mean that the eerie connectedness of the quantum realm is not a small-scale curiosity, but a fundamental feature of the entire universe, with the cosmic web as its most visible manifestation. The filaments would then be more than just highways for galaxies. They would be the physical threads of a quantum tapestry, connecting the cosmos in a way we are only beginning to imagine. Yet for all the grand, sweeping motions of galaxies and the invisible pull of the great attractor, our journey through the cosmic web must also confront the profound mystery of its opposite, the staggering, almost inconceivable emptiness of the great voids. If filaments are the crowded highways of the cosmos, then voids are the immense, silent deserts that stretch between them. And of all these cosmic deserts, one stands out as the most baffling and expansive of all, the Borealis void. To call it a void is almost an understatement. It is a cavern of nothingness so vast it has earned the ominous nickname, the Great Nothing. Picture a sphere of space roughly 250 million light-years across. Within a volume this immense, our standard models of the universe predict it should contain thousands of galaxies, perhaps even 10,000. The Borealis void contains only 60. That's not just a little underdense, it is a staggering, near-total emptiness. If our Milky Way were located at the center of the Borealis void, and if human civilization had arisen there, we would not have known other galaxies existed until the 1960s. Our entire night sky, absent the stars of our own galaxy, would be an unbroken, profound blackness. The nearest major galaxy would be so far away its light would be a barely perceptible smudge. The immediate, obvious question is how such a place could possibly form. The prevailing theory of structure formation, based on the gravitational collapse of dark matter, does allow for voids. Regions that start out ever so slightly less dense than their surroundings see their matter slowly drained away over billions of years by the gravitational pull of emerging filaments and clusters. They are the valleys to the mountain ranges of the cosmic web. But the scale of the Borealis void is so extreme that it strains this theory to its breaking point. It is not a valley, it is a bottomless chasm. There simply hasn't been enough time since the Big Bang for gravity to have evacuated such an enormous volume of space so completely. It is a structure that, by our current understanding, shouldn't be able to exist. This forces cosmologists to consider two radically different possibilities. The first is that we are the witnesses to a statistical fluke of almost impossibly bad luck, unnatural, but incredibly rare, fluctuation in the density of the early universe that created a single, gigantic bubble of near-nothingness. The odds of such a fluctuation occurring are astronomically low, but in an infinite or near-infinite universe, the nearly impossible must happen somewhere. In this view, the Borealis void is just that somewhere. We happen to live next door to a cosmic unicorn. The second possibility is far more exciting, that the void is not a fluke, but a signpost for physics we have not yet discovered. Perhaps the void was carved out by something more violent and dynamic than mere gravitational evolution. One speculative theory involves the influence of dark energy, the mysterious force accelerating the universe's expansion. Could dark energy behave differently in these extremely low-density environments, becoming stronger and actively pushing out any remaining matter, effectively inflating the void from within? Or could the void be the scar of a primordial collision between our universe and another bubble universe in the multiverse, a collision that cleared out everything in its path? The few galaxies that do reside within the Borealis void add another layer of intrigue. They are not randomly scattered. Many of them appear to be aligned into a loose, tube-like structure that cuts through the center of the void. This faint filament within a void suggests that even in this great desert, the underlying architecture of the cosmic web is still faintly present, like the ghost of a riverbed in a parched landscape. Studying these isolated galaxies is like studying life in the deepest trenches of the ocean. They are evolutionary outliers. Have they been starved of interactions, becoming quiet backwaters? Or did they form under such unique conditions that they hold secrets about galaxy formation we can't learn anywhere else? The Borealis void is more than an empty space. It is a profound question mark. Its existence challenges the statistical predictions of our cosmological models and dares us to find a mechanism capable of creating such epic nothingness. It is a reminder that the cosmic web is a tapestry of both incredible density and unbelievable emptiness, and that understanding the voids may be just as important to decoding the universe's history as understanding the glittering clusters and filaments themselves. But even as we confront the vast emptiness of the Borealis void, we must also turn our attention to a paradox that lies in the very substance of the cosmic web itself. Zoom in on one of these immense filaments, and you'd expect to find a relatively smooth and homogeneous river of gas, a simple, flowing conduit of matter. After all, this intergalactic medium has been expanding and cooling for billions of years, and the powerful forces of gravity and dark matter should have sculpted it into a predictable, diffuse flow. Our most sophisticated supercomputer simulations of the universe, which are built upon our standard models of cosmology and dark matter, predict exactly that, a smooth distribution of gas within these cosmic tendrils. However, when astronomers finally developed the tools to peer into these filaments with incredible resolution, they were met with a sight that defied all expectations. The gas isn't smooth at all. Instead, it is clumpy, it is frothy. It is filled with pockets of higher and lower density, like a river teeming with invisible whirlpools and eddies. This is the filament gas clumping paradox, and it represents a direct challenge to our most fundamental assumptions about how the universe works on the largest scales. To understand why this is so baffling, we need to appreciate the sheer timescales and forces involved. The gas within these filaments has been traveling for eons, flowing along the gravitational landscape defined by the dark matter skeleton of the cosmic web. Over such immense periods of time and across such vast distances, any initial small-scale turbulence or clumpiness should have been smoothed out by the universe's expansion and by the relentless pull of gravity. The standard model, known as lambda cold dark matter, assumes that dark matter is cold, meaning its particles move relatively slowly and that it only interacts through gravity. This model has been spectacularly successful at predicting the large-scale structure of the cosmos, the distribution of galaxies, and the patterns in the cosmic microwave background. But it predicts a much calmer, more uniform distribution of gas within filaments than what we actually observe. The clumpiness we see is a small-scale detail that the model completely misses, suggesting a critical flaw in our understanding of the physics at play within these environments. So what could be causing this unexpected frothiness? The first and most conservative explanation points to feedback from galaxies. As we've discussed, galaxies are not passive passengers on the cosmic web, they are active engines. Supernova explosions and violent outbursts from supermassive black holes can blast enormous bubbles of hot gas out of their host galaxies and deep into the surrounding filament. This injected energy could stir up the placid river of gas, creating the localized clumps and irregularities we detect. It's like tossing a handful of stones into a calm stream. The resulting ripples and disturbances would create a more complex, turbulent structure. This is a compelling idea, and it almost certainly contributes to the effect. However, when astronomers go looking for the culprits, they often find a crime scene with not enough witnesses. In many filaments, there simply aren't enough active galaxies to account for the pervasive and widespread clumping that is observed. The energy required to churn the entire length of a filament is immense, and the galactic engines don't seem to be powerful enough to do the job. This failure of conventional explanations forces us to consider more exotic possibilities, and once again, the spotlight turns to the enigmatic nature of dark matter. The standard model assumes dark matter is cold and non-interacting, but what if it's not? What if dark matter particles can interact with each other through some unknown force, a so-called dark force that is distinct from gravity? This concept, often called self-interacting dark matter, could provide an elegant solution to the paradox. Within a filament, these dark matter particles wouldn't just pass through each other like ghosts, they could collide and scatter. This interaction would create a form of friction or viscosity within the dark matter itself, which would then imprint onto the normal gas through gravity, causing it to churn and form the very clumps we observe. In this scenario, the frothiness of the gas is a direct window into the hidden physics of the dark sector, a visible echo of invisible particles bumping into each other in the dark. Another radical idea involves the universe's expansion and the nature of dark energy. Could the accelerating expansion of the universe, driven by dark energy, be causing these filaments to stretch and strain in a way that introduces turbulence? Or perhaps the magnetic fields that permeate these structures, whose origins we still don't understand, are playing a role in confining and shaping the gas into these lumpy formations. Each of these possibilities points to a gap in our knowledge, a missing piece of physics that our current simulations do not include. The filament gas clumping paradox is not a minor detail, it is a potentially crucial clue. The way gas behaves on these small scales within the large-scale cosmic web directly influences how galaxies form and evolve. The density of these clumps determines how easily gas can cool and collapse to form new stars, and how efficiently it can be funneled into growing galaxy clusters. By getting this detail wrong, we might be misunderstanding a critical part of the cosmic life cycle. This seemingly technical discrepancy is therefore a gateway, compelling us to question the very properties of the universe's most dominant but mysterious components. And just as the axis of evil challenges our view of the cosmos from a preferred direction, an even more fundamental pattern emerges when we analyze the very first and largest ripples in the fabric of space-time. To understand this, we need to delve deeper into the language we use to read the cosmic microwave background. Scientists don't just look at the hot and cold spots as a simple picture. They translate the entire map into a mathematical symphony of waves, a technique known as a multipole expansion. Each multipole represents a different scale of fluctuation. The dipole is the largest, caused mostly by our own motion through the universe. The quadrupole and octupole come next, representing the next largest possible waves, patterns that stretch across the entire sky. According to our standard model, these primordial patterns should be completely random, the result of quantum noise frozen into the universe during inflation. They should have no relation to each other, no common alignment, and certainly no connection to our local solar system. Yet, when researchers analyzed the data, they found that the quadrupole and octupole are not random at all. They are strangely aligned with each other, and even more perplexingly, this shared alignment also correlates with the ecliptic plane of our solar system and the direction of the axis of evil. This is a mystery that cuts even closer to the bone than its predecessor. The quadrupole and octupole are among the very largest possible structures we can measure in the universe, patterns imprinted when the cosmos was smaller than a proton. The idea that their orientation could have anything to do with the plane in which Earth orbits the Sun, an arrangement that wouldn't exist for billions of years, is so logically absurd that it must be a terrible mistake or a profound clue. The immediate and most persistent explanation from the scientific community is that this is a systematic error, an artifact introduced by the way we process the data. Perhaps our models for subtracting the foreground glow of our own galaxy's dust and gas are imperfect, inadvertently leaving behind a contaminating signal that mimics this strange alignment. The teams behind the Planck and WMAP satellites have tirelessly worked to eliminate every conceivable source of error, refining their methods to an incredible degree. Yet the alignment persists. It's a signal that refuses to be cleaned away, a stubborn ghost in the data that haunts our most precise measurements of the infant universe. If we dare to entertain the possibility that the signal is real, the implications are nothing short of revolutionary. It would suggest that the universe is not isotropic and homogeneous on the largest scales, directly contradicting the cosmological principle that has guided astronomy for a century. But it points to something even more radical, a potential memory of a time before the Big Bang. Our standard model describes a beginning from a singularity, a point of infinite density where all known laws of physics break down. It offers no before, but the alignment of these largest modes could be a clue that our universe inherited a preferred direction from a prior state of existence. Some speculative cosmological models, like conformal cyclic cosmology or theories involving a bouncing universe, propose that our cosmos is one in a cycle. In such a model, the alignment of the largest scales could be an echo, a fossilized imprint of a previous cosmic eon's rotation or structure, carried over through the transition of the Big Bang. It would be a cosmic memory, a scar from a universe that once was. Another extraordinary possibility is that the alignment is evidence of a rotating universe. Einstein's general theory of relativity does not forbid a cosmos with an overall spin, though it would require significant modifications to our current models. A universal rotation would create a preferred axis, a cosmic north and south pole, around which everything would turn. This rotation would then naturally imprint itself on the first light emitted, aligning the quadrupole and octupole modes. While there is no other evidence to support this idea, the persistent alignment remains a tantalizing, if controversial, hint. The CMB quadrupole and octupole alignment is perhaps the most subtle and technical of the anomalies we've explored, but it may also be the most profound. It doesn't point to a missing object or a strange flow, but to a potential flaw in our very understanding of the origin and fundamental geometry of everything that exists. It is a whisper from the earliest possible moment, suggesting that the first light of creation still holds secrets about where we came from, and that the universe may have a memory far older than we ever thought possible. But the story of cosmic chemistry is far from complete, and the plot is about to take another unexpected turn. If we journey beyond the well-mapped territories of galaxy clusters and into the more diffuse rivers of the cosmic filaments themselves, we encounter a compositional mystery that challenges our very understanding of where the universe's elements are forged. According to our established stellar law, the specific blend of heavy elements, the cosmic DNA left behind by different types of stellar explosions, should act as a clear fingerprint. The violent demise of a massive star in a core collapse supernova leaves one distinct pattern of elements, rich in alpha elements like oxygen, neon, and magnesium. The titanic thermonuclear detonation of a white dwarf star, a Type Ia supernova, leaves a very different signature, overloading its surroundings with iron group elements like iron and nickel. For decades, astronomers have used these chemical fingerprints to reconstruct the history of star formation within galaxies, confident that the models of nucleosynthesis were reliable guides. However, when scientists began to use the most powerful telescopes to perform a delicate chemical analysis of the gas within the cosmic filaments, the very backbone of the web, they uncovered a puzzle that rewrites the recipe book. By observing the faint absorption lines imprinted on the light of distant quasars as it passes through these filamentary structures, they can measure the abundance of various elements within that diffuse intergalactic gas. The results are baffling. The ratios of key elements, particularly the balance between iron and the alpha elements, do not match the expected yields from either type of supernova. In many regions, the gas appears to be enriched with a bizarre overabundance of iron, far more than the standard supernova models can account for. It's as if we've analyzed the alloy of a steel beam in a modern skyscraper and found a composition that no known smelting process on Earth could possibly produce. This unexpected elemental abundance forces a profound reconsideration of the universe's primary forges. The sheer quantity of iron suggests a dominant role for Type Ia supernova, but the observed patterns still don't align perfectly with their predicted yields. This discrepancy points to the possibility that our understanding of these colossal explosions is incomplete. Perhaps there are multiple pathways to a Type Ia event, some of which produce a much greater iron output than our current models allow. Or, more excitingly, it suggests that we might be seeing the signature of an entirely different and far more exotic nucleosynthesis engine. One compelling candidate is the collision of two ultra-dense neutron stars, a cataclysmic event known as a kilonova. These mergers are known to be factories for the heaviest elements in the periodic table, like gold and platinum, but they also blast out significant amounts of iron and other material. Could it be that kilonovae are far more common contributors to the cosmic pollution than we ever imagined? Their debris flung far and wide into the filaments by the immense forces of the explosion. Another radical idea involves the very nature of the first stars. The population Roman 3 stars, the universe's pristine first generation, are thought to have been colossal behemoths, hundreds of times more massive than our Sun. Their deaths in hypernova explosions would have been unlike anything we see today, potentially yielding a unique cocktail of elements that could explain the anomalous ratios we detect billions of years later in the filaments. While these first stars themselves are long gone, their chemical legacy might be preserved in these vast intergalactic reservoirs, a ghostly signature waiting to be decoded. The cosmic filaments, therefore, are not just passive conduits. They are a historical archive storing a mixed record of every violent event that has ever contributed material to the intergalactic medium. The puzzling abundances we find today are the blended echoes of all these events, a complex symphony of destruction that we are only just learning to hear. This mystery has direct consequences for the future of cosmic structure. The specific mix of elements governs how efficiently gas can cool and collapse to form new generations of stars and galaxies. An overabundance of certain elements can dramatically alter the thermal properties of the gas, either catalyzing or quenching the birth of new stars in the filaments themselves. The fact that we cannot yet reliably trace the origin of these elements means we are missing a fundamental chapter in the story of how the cosmic web evolves. It reveals that the life cycle of matter, from its creation in stellar furnaces to its distribution across the universe, is a more complex and wondrous process than our textbooks have yet captured. And now we arrive at a mystery that hits remarkably close to home, suggesting that our entire cosmic neighborhood might be skewing our perception of the universe's expansion. This brings us to the KBC void, named for astronomers Keenan, Barger, and Cowie, and its potential role in the Great Hubble tension. For all our talk of the cosmological principle, the idea that the universe is largely uniform, what if we, the observers, are actually sitting in a special place? Not a center of the universe, but a location of significant underdensity, a local bubble of nothingness that is distorting our measurements. The KBC void proposal suggests exactly that, Our local group of galaxies resides inside one of the largest cosmic voids ever identified, a spherical region nearly 2 billion light-years across where the density of matter is significantly lower than the cosmic average. Think of it like this: you're standing in a valley trying to measure the steepness of the surrounding mountains. Your perspective from that low point will make the mountains appear much taller and steeper than they would to someone standing on a plateau. In the same way, if we are inside a vast underdense region, the gravitational dynamics are radically different here than in the average universe. The lower density means there is less matter to gravitationally tug on us and our nearby galaxies, effectively reducing the local gravitational brake on expansion. From our vantage point inside this void, it would appear that the space around us is expanding faster than it actually is in the denser regions outside, because we are experiencing less gravitational resistance to the push of dark energy. This local speed-up could perfectly explain why our measurements of the Hubble constant using nearby supernova give a higher value than the predictions from the early universe, which average over the entire cosmos. The implications of this are staggering. If true, it means the Hubble tension isn't a sign of new physics after all, but simply a colossal error of perspective. It would be a cosmic illusion on a billion light-year scale. This idea offers an elegant, albeit humbling, solution. We wouldn't need to invoke evolving dark energy or new types of particles. We would just need to acknowledge that our local patch of space is not typical, forcing us to apply a correction factor to our local measurements to find the true global expansion rate. For many, this is a deeply attractive proposition because it resolves the tension without overthrowing the incredibly successful standard model of cosmology. However, the KBC void is not without its own profound problems. Its proposed size is the first and greatest issue. A void 2 billion light-years in diameter pushes right up against and likely exceeds the theoretical maximum size allowed by the standard model of structure formation. Just like the Borealis void, creating such an immense emptiness through gravitational evolution alone in the age of the universe is incredibly difficult. The odds of such a void forming naturally are exceedingly low. This means that to solve one problem, the Hubble tension, we might be creating another, equally severe problem, the existence of a void that itself shouldn't be possible. Furthermore, the evidence for the void's existence is still contested. While some large-scale surveys of galaxy distributions do show a notable underdensity in our local universe, others argue that the statistical significance is not yet strong enough to confirm a void of the required scale and emptiness. The debate is fierce. If we cannot definitively prove the void's existence and properties, then it remains an interesting but unverified hypothesis, a potential ghost that could explain the tension but might itself be a mirage. Ultimately, the KBC void hypothesis forces a profound philosophical choice. Do we abandon the cosmological principle, at least locally, and accept that we live in a slightly special place that has tricked us? Or do we cling to the principle and assume the tension must therefore be evidence of new, exotic physics? Both options are revolutionary in their own way. One suggests our maps are wrong because our location is biased. The other suggests our maps are right and our laws of physics are incomplete. The KBC void stands as a tantalizing reminder that before we can truly understand the universe, we must first understand our place within it and how that position might be coloring our view of cosmic reality. Yet for all the mysteries we find in the ordinary matter, its unexpected temperatures, its puzzling chemistry, its frothy clumpiness, the greatest enigma of all remains the behavior of the dark matter that should be holding everything together. According to our foundational lambda cold dark matter model, the cosmic web is primarily a creation of dark matter. It predicts a specific hierarchical structure. The lion's share of dark matter should be concentrated in dense, spherical halos around galaxies, and even more so in the massive nodes where filaments meet at galaxy clusters. The filaments themselves were thought to be mere bridges, simpler rivers of dark matter flowing between these reservoirs with a relatively smooth and predictable density gradient. This picture is the bedrock of modern cosmology, the result of decades of sophisticated computer simulations that beautifully replicate the large-scale structure we see. But when astronomers finally developed methods to map the actual distribution of dark matter within these filaments, they found a reality that refuses to conform to the simulation. The primary tool for this cosmic cartography is gravitational lensing, the phenomenon where the gravity of a massive object like a filament warps the fabric of space-time, distorting the light from background galaxies like a funhouse mirror. By meticulously measuring the subtle, telltale stretch of thousands of these distant galaxies, we can reconstruct a map of the mass both seen and unseen along our line of sight. Applying this technique to the cosmic filaments has revealed a startling anomaly. The dark matter within these structures is not distributed as a smooth, declining gradient from the cluster outward. Instead, it appears to be clumped. It forms subhalos, smaller knots, and concentrations of invisible mass embedded within the larger filamentary stream. This is a direct contradiction to the predictions of the standard lambda cold dark matter model, which expects dark matter to be far more smoothly distributed on these scales. It's as if we expected to find a wide, calm river, but instead discovered a waterway choked with invisible icebergs. This discovery sends shockwaves through the field because it challenges the very properties we have assigned to dark matter. The standard model assumes dark matter is cold, meaning its particles move slowly, and collisionless, meaning they rarely, if ever, interact with each other or with normal matter except through gravity. This is why it forms those smooth, massive halos. The particles simply flow along gravitational contours without any friction to cause clumping on smaller scales within filaments. The observation of these subhalos suggests that dark matter might not be as simple or as inert as we thought. Perhaps it possesses a little more complexity, a subtle ability to interact with itself through some unknown force other than gravity. This concept, known as self-interacting dark matter, could provide an elegant explanation. If dark matter particles can bump into each other, that microscopic friction could cause them to slow down and congregate into the very clumps we detect through lensing. This wouldn't be a violent collision, but a gentle nudge, enough to slightly alter their distribution from the pristine predictions of the simplest models. The implications of this possibility are enormous. It would open up a whole new, dark sector of physics with its own rules and forces operating in parallel to our own. But this is not the only radical interpretation. The other, even more paradigm-shifting conclusion is that we may not need dark matter at all. The anomalous distribution could be a glaring sign that our understanding of gravity itself is flawed. Alternative theories of gravity, most notably modified Newtonian dynamics or MUND, were originally proposed to explain the rotation curves of individual galaxies without invoking dark matter. They suggest that gravity behaves differently at extremely low accelerations, like those found in the outskirts of galaxies. For decades, cosmologists argued that MUND failed to explain the observed behavior of galaxy clusters and the large-scale structure of the cosmic web. However, the persistence of these filamentary anomalies has given new life to these ideas. Proponents of modified gravity argue that the apparent clumping of mass within filaments could be a natural outcome of their equations, a direct prediction rather than a problem to be solved. In this view, the lensing map is showing us the true distribution of mass as dictated by a new law of gravity, and the dark matter subhalos are merely phantoms, illusions created by our insistence on applying Einstein's rules in a realm where they no longer hold sway. This leaves us with a profound and unresolved tension at the heart of cosmology. Do we preserve dark matter and complicate its physics, endowing it with new properties to explain these small-scale structures? Or do we tear down the foundational pillar of late 20th century cosmology and rewrite the laws of gravity to account for the universe's behavior? The cosmic filaments, acting as immense natural laboratories, are where this battle is being fought. Their faint, lensing distortions hold the key to understanding whether the universe is dominated by a hidden, complex form of matter we cannot see, or if the force that binds the cosmos together is far more mysterious than we ever allowed ourselves to believe. Yet, even as we grapple with the distribution of dark matter, we encounter a mystery that strikes at the very laws governing the universe's most energetic particles. This enigma begins not in the silent depths of a void, but with a cosmic bullet screaming into our atmosphere from the depths of intergalactic space. These are ultra-high-energy cosmic rays, and they are the most energetic particles ever detected. A single one can carry the kinetic energy of a well-thrown baseball, but compressed into a single subatomic proton. For decades, physicists have had a firm theoretical limit on just how energetic such a particle can be when it arrives from a distant source. This limit is known as the GZK cutoff, named for physicists Greisen, Zatsepin, and Kuzmin, and it represents a fundamental speed limit imposed by the fabric of space itself. The logic behind this cutoff is beautifully simple, and for a long time it was considered unbreakable. Imagine one of these proton bullets traveling across the universe for hundreds of millions of light years. On its immense journey, it is not moving through empty space. It is moving through a universe filled with the faint, relic photons of the cosmic microwave background, the afterglow of the Big Bang. While these photons are incredibly low energy, for a proton traveling at over 99.9% the speed of light, even this faint background radiation becomes a formidable barrier. Each collision between the ultra-fast proton and a background photon is like a car windshield hitting a stationary bug at relativistic speeds. According to Einstein's special relativity, these collisions should sap the proton's energy, slowing it down significantly over long distances. The GZK cutoff calculates that no proton should be able to reach Earth with an energy greater than about 6 times 10 to the 19th electron volts if it has traveled more than 160 million light years. It's a cosmic speed limit that should be utterly unforgiving, but nature, it seems, loves to break its own rules. On multiple occasions, enormous cosmic ray observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah have detected particles that smash right through this theoretical limit. These are the violators, cosmic rays with energies so stupendously high that they should not exist if our understanding of physics is correct. The most baffling part is that when astronomers have tried to trace the paths of these rule-breaking particles back to their source, they often point to distant active galaxies or quasars located far beyond the 160 million light-year safe zone. According to the GZK process, any proton originating from such a distance should have been slowed down by its constant battle with the cosmic microwave background long before it ever reached us. The fact that it arrived with its immense energy intact is not just a surprise, it is a direct challenge to established physics. This presents scientists with a thrilling and deeply perplexing dilemma. The first and most conservative explanation is that we are misidentifying the particles. Perhaps these ultra-high-energy messengers are not protons at all, but heavier atomic nuclei like iron. A nucleus with its greater mass and charge would interact differently with the background radiation and could potentially retain its energy over a longer journey. However, when researchers analyze the showers of secondary particles these cosmic rays create in the atmosphere, their structure often doesn't match the expected signature of a heavy nucleus. The evidence continues to point toward a proton, the very particle the GZK cutoff was designed for. If the particle identification is correct, then we are forced to consider far more radical possibilities. One extraordinary idea is that these particles are not protons but something entirely new, an exotic, stable massive particle that has yet to be discovered, which does not interact with the cosmic microwave background in the same way. This hypothetical traveler could be a relic from the early universe, a piece of primordial physics that has been flying through the cosmos undeterred by the obstacles that would stop a normal proton. Another, even more mind-bending possibility is that our understanding of special relativity itself requires a subtle modification at these extreme energies. Theories like doubly special relativity propose tiny alterations to the laws of physics at energies approaching the Planck scale, which could effectively raise or remove the GZK cutoff. This would mean that the universe's speed limit signs are written in a language we don't yet fully understand. The most profound implication, however, touches upon the very nature of space and time. Could these particles be shortcuts through the cosmos? If space-time possesses a quantum foam-like structure at the smallest scales, perhaps these ultra-high-energy particles are interacting with it in a way that effectively reduces the distance they have traveled, allowing them to avoid the countless interactions that would normally drain their energy. Or perhaps they are a sign of extraspatial dimensions, as predicted by string theory, which could provide unseen pathways that allow the particles to bypass the resistive effects of the background radiation. Each detected violation of the GZK cutoff is a message from the far reaches of the universe, carried by a particle of impossible energy. It tells us that the cosmic web is not only a structure of matter and gravity, but also a highway for phenomena that defy our current physical models. These rare events are like cosmic lightning strikes, illuminating for a brief moment the frontiers of our knowledge, and revealing just how much we have yet to learn about the fundamental rules that govern the journey of matter across the vastness of space. But the strange behavior of ultra-high-energy cosmic rays is not the only phenomenon hinting that the cosmic web might be governed by rules beyond our standard model. As we zoom out to study the web's grand architecture, an even more subtle and profound mystery emerges from the statistics of its connections. When cosmologists map the universe on the largest scales, they don't just see a random scatter of galaxies. They see a network, and like any network, it can be analyzed. Scientists apply the mathematical tools of graph theory, treating galaxies as nodes and the filaments between them as edges. This allows them to quantify the web's structure, measuring its connectivity, the distribution of node links, and the presence of specific topological patterns. According to our standard model of cosmic evolution, which is driven by gravitational collapse and random initial quantum fluctuations, these connectivity patterns should be, for the most part, random. There should be no hidden order, no repeating motifs, no statistical signature that can't be explained by gravity and chance alone. Yet, that is not what the data reveals. In the precise maps generated by massive galaxy surveys, researchers have begun to identify faint but persistent statistical anomalies in how galaxies link up within the filaments. Certain specific configurations, certain ways that nodes connect to form chains or clusters within the web, appear with a slightly higher frequency than the standard model predicts. It's a subtle effect, like finding that a handful of words appear just a little too often in a book that was supposedly written by randomly shaking letters in a bag. This isn't about the overall shape of the web, which our models get right, but about the fine-grained architectural details within it. The gravitational playbook, which has been so successful at explaining the universe's large-scale structure, seems to be missing a page when it comes to these intricate connection patterns. This has led a growing number of theoretical physicists to propose a truly radical explanation, that these anomalous connectivity patterns are the first observable hints of quantum gravity effects operating on a cosmic scale. Quantum gravity is the holy grail of modern physics, the sought-after theory that would unite Einstein's theory of general relativity, which governs the very large, with quantum mechanics, which governs the very small. All attempts to create such a theory, like string theory or loop quantum gravity, predict that on the tiniest possible scale, the Planck length spacetime is not smooth and continuous but granular or foamy. This quantum foam is a seething ocean of virtual particles popping in and out of existence, with tiny wormholes and quantum fluctuations that momentarily warp the fabric of reality. We have always assumed these effects are negligible on scales larger than a subatomic particle, utterly wiped out by the averaging of trillions upon trillions of such events. But what if they aren't completely erased? What if, in the immense gravitational potentials of the cosmic web's dark matter skeleton, these tiny quantum effects can be amplified or perhaps entangled across vast distances, leaving a faint statistical imprint on how the web assembles itself? In this speculative view, the cosmic web is not just a gravitational structure but also a quantum computational one. The initial quantum fluctuations that seeded the web were not entirely random. They contained within them the non-local correlations and entanglement that are the hallmark of quantum mechanics. As the universe expanded and these fluctuations were stretched to cosmic sizes, that underlying quantum connectedness could have subtly influenced the gravitational collapse process, predisposing matter to form certain network patterns over others. The filaments, in this sense, might be the physical manifestation of primordial quantum entanglement, with their connectivity patterns reflecting a hidden quantum code written into the universe at its birth. It would mean that the spooky action at a distance that so troubled Einstein didn't just vanish. It was woven into the cosmos's largest structures, operating in slow motion across billions of light years. Of course, this idea remains highly controversial and is far from being accepted mainstream science. Skeptics argue, quite reasonably, that the observed statistical anomalies could easily be the result of unknown systematic errors in our galaxy surveys or oversimplifications in our complex computer simulations of structure formation. Perhaps ordinary astrophysical processes, like the way galactic winds or radiation from early stars can affect gas collapse in neighboring regions, could create these subtle correlations without needing to invoke quantum gravity. The burden of proof is immense, as it requires not only confirming the anomaly beyond any doubt, but also conclusively ruling out every possible conventional explanation. Yet, the mere fact that such an extraordinary idea is being seriously debated highlights the depth of this mystery. The cosmic web is the largest pattern in nature, and if its finest details are hinting that our two most successful but incompatible theories of physics are somehow speaking to each other across an unimaginable gulf of scale, then we are on the verge of a revolution in understanding. These connectivity patterns are a potential Rosetta Stone, a way to translate the language of quantum mechanics into the language of cosmology. By continuing to map the universe with ever greater precision, we are not just cataloging galaxies, we are running a cosmic experiment, testing whether the fabric of spacetime itself has a hidden grain, a quantum texture that guides the hand of creation. And just when we thought the cosmic web couldn't present a more fundamental challenge, we arrive at a phenomenon that strikes at the very heart of how we measure the universe and tests one of the most cherished principles in all of physics. This is the Etherington distance duality tension, a deeply technical-sounding mystery that carries profound implications. At its core is a beautifully simple prediction made by general relativity known as the distance duality relation. It states that two methods of measuring the distance to a celestial object should always, and without exception, agree. The first method relies on geometry, watching how an object's apparent size changes with distance, much like a car appearing smaller as it drives away. The second method is based on light, specifically how the brightness of an object dims as it recedes from us. According to Einstein's theory, bolstered by the fundamental conservation of photons, these two measurements are two sides of the same coin. They are cosmologically equivalent and must yield the same result. It's a foundational pillar as solid as the laws of thermodynamics. To test this, astronomers turn their most powerful instruments toward the cosmic filaments. These vast structures provide a perfect laboratory because they are filled with hot, ionized gas that emits X-rays, and they are also backlit by the brilliant, steady glow of distant quasars. By observing the filament in X-rays, we can measure its physical size and calculate a geometric distance. Simultaneously, by studying how much the quasar's light is dimmed and reddened as it passes through the filament, we can calculate a luminosity distance. In a universe that obeys the rules, these two numbers should be identical. Yet, in an increasing number of studies, they are not. The measurements taken within these cosmic tendrils consistently show a small but stubborn discrepancy. The luminosity distance and the geometric distance refuse to agree, creating a tension that, on the surface, should not exist. This places cosmologists in an incredibly difficult position. A violation of the distance-duality relation is not like finding a new, strange particle. It is a direct assault on the consistency of general relativity itself and on the principle of photon conservation. The immediate and most palatable assumption is that the error lies with us. Perhaps our observations are being contaminated by unknown astrophysical effects within the filaments themselves. Could it be that the gas is clumpier than we think, or that there is an unexpected amount of dust intermixed with the plasma, selectively absorbing certain wavelengths of light and tricking our instruments? Maybe the quasars we use as background lights are not perfectly steady beacons, but flicker in ways we haven't accounted for. Decades of work have been dedicated to hunting down these potential systematic errors, refining the models of the intra-filament medium to exquisite detail. Yet the discrepancy persists, refusing to be explained away by conventional astrophysics. This forces us to confront far more radical possibilities. The first is that our understanding of gravity is incomplete. While general relativity has passed every test thrown at it with flying colors for a century, its validity across the vast, diffuse scales of a cosmic filament is less certain. Could there be a subtle modification to gravity's behavior in these low-density environments that subtly alters the paths of photons or the geometry of space in a way that breaks the distance duality? The other, even more profound possibility is that photons are not conserved over these epic journeys. The notion that light simply travels through the void, unchanging and eternal, is a bedrock assumption. But what if it's wrong? What if photons can slowly decay into very light, undiscovered particles like ultra-light actions over billions of light years? Or perhaps they can interact ever so slightly with the dark energy that permeates the void, losing a tiny fraction of their energy in a way that mimics extra distance traveled. These ideas were once the domain of pure speculation, but the persistent tension in the filaments is giving them tangible, observational weight. The Etherington tension is a masterclass in scientific humility. It shows us that even our most trusted tools for mapping the cosmos might be giving us subtly flawed readings, and that the most basic assumptions like the constancy of a photon's journey might need to be re-examined in the strange, expansive laboratory of the cosmic web. It is a quiet, statistical whisper from the data, suggesting that the universe's deepest secrets might be hidden not in the grand explosions, but in the slightest of disagreements between how we think the light should behave and what the light is actually telling us. Yet, as we chart the cosmic web across the vastness of space, we are also mapping it back through time, and here we find a profound contradiction emerging from the early chapters of the universe's story. According to our standard model of cosmic evolution, the immense architecture we see today grew slowly and methodically over billions of years. It began with the faintest of ripples in the fabric of the newborn universe, tiny quantum fluctuations that were stretched to cosmic proportions during a period of hyper-expansion called inflation. Over the ensuing eons, gravity acted as a patient sculptor, gradually pulling matter into denser knots, with the first small filaments only beginning to form after several 100 million years. The first massive galaxy clusters, the dense nodes where filaments intersect, should have taken even longer to assemble, their full maturity not reached until the universe was many billions of years old. This timeline is a core prediction of our cosmological models, and it has been supported by powerful computer simulations that beautifully recreate the universe we see around us. But the universe, it seems, did not read the script when astronomers trained their most powerful telescopes on the most distant, and therefore the youngest, observable regions of space. They are essentially looking back in time. They can see the universe as it was when it was only a fraction of its current age, and in this ancient light they are finding fully formed cosmic filaments and massive galaxy clusters that by all rights should not be there. These structures are cosmic precocious children, appearing in the nursery of the early universe billions of years earlier than our models say they should have. It's the equivalent of archaeologists digging up a modern skyscraper in a layer of earth dated to the Bronze Age. The sheer maturity and complexity of the structure completely upends our understanding of the timeline of technological development. In the cosmic context, we are finding the skeletal framework of the universe already in place when it was far too young for such advanced construction. This discovery of an unexpectedly mature early universe creates a serious problem for our theory of cosmic structure formation, which is built upon the twin pillars of dark matter and dark energy. The prevailing model, known as lambda cold dark matter, relies on dark matter's gravity to provide the initial scaffolding. But for this scaffolding to assemble into such vast, coherent structures so quickly, the process would have had to be far more efficient than we currently believe. The dark matter would need to have clumped together with astonishing speed, pulling normal matter along with it at a pace that seems to defy the gradual, relentless crawl of gravitational collapse. This has led scientists to question the very properties of dark matter. Perhaps it is not completely cold. Maybe its particles had a little more thermal energy or velocity in the early universe, allowing them to move and aggregate faster. Or more radically, perhaps dark matter can interact with itself through some unknown force, a kind of dark physics that accelerates the clumping process beyond what simple gravity can achieve. But dark matter is not the only suspect. The other pillar of our model, dark energy, also comes under scrutiny. In our standard view, dark energy is a constant force, a latent pressure inherent to the vacuum of space that only began to dominate the universe's expansion several billion years ago. However, if dark energy were not constant but instead varied in strength over time, its influence on the early expansion history could have been profoundly different. A weaker dark energy in the ancient past would have allowed gravity to work more effectively for a longer period, potentially fast-tracking the formation of these giant structures. Alternatively, some theorists propose that our understanding of gravity itself needs revision on these largest scales. Modifications to Einstein's theory of general relativity could introduce extra terms that enhance gravitational attraction in the low-density environments of the early universe, providing the extra pull needed to build cities of galaxies at breakneck speed. The implications of this early formation are staggering, reaching far beyond a simple tweak to a cosmological parameter. If the cosmic web was already well established when the universe was in its infancy, it means the conditions for galaxy formation and evolution were set in place much earlier than we thought. The first galaxies would have been born into a ready-made network of filaments, their growth and interactions shaped and accelerated by this pre-existing architecture. This could explain the existence of incredibly massive, bright galaxies observed at very high redshifts, objects that themselves seem to have formed too quickly. The early web would have acted as a cosmic conveyor belt, efficiently funneling gas into hungry young galaxies and fostering the rapid birth of stars and black holes. The timeline of cosmic dawn, the period when the first stars and galaxies lit up the universe, may need to be completely rewritten, pushed back into a denser, more dynamic, and far more structured early cosmos than we ever imagined. And now we arrive at a discovery that turns the very idea of cosmic motion on its head, challenging the fundamental tenet that gravity is only an attractive force. For centuries, we have understood the universe's dance as one of pure pull massive objects exerting a gravitational tug that draws everything together. But what if we've been missing half the story? What if, hidden in the vast expanses between the glittering filaments, there exists a force not of attraction but of repulsion? This brings us to our final and perhaps most conceptually challenging phenomenon, the mystery of the dipole repeller. Our story begins not with a mysterious push but with a well-documented pull. As we discussed earlier, our local group of galaxies is caught in a powerful current, flowing toward the immense gravitational attractors like the Shapley supercluster. For decades, cosmologists mapped this motion by focusing on what was pulling us, but a team of researchers led by astronomer Yehuda Hoffman decided to approach the puzzle from the opposite direction. Instead of just asking what was pulling us, they asked a more complete question: what is pushing us? Using sophisticated models of galaxy motions and the most detailed maps of the nearby cosmic web from surveys like the Cosmic Flows project, they began to trace the flow not just toward the attractors but away from something else. Their calculations revealed that to fully explain the velocity and direction of our motion, a significant component had to be a repulsive force. The math pointed to a vast, incredibly empty region of space in the opposite direction of the Shapley attractor, a place so devoid of matter that its effective gravity isn't just neutral, it's negative. They named this region the dipole repeller. The mechanism behind this apparent repulsion is a masterpiece of cosmic irony. It isn't that gravity itself has reversed, Einstein's law still holds. Instead, it's the staggering emptiness of the repeller that creates the effect. Imagine you're in a boat on a wide, calm lake. If you're near a shore, the water's edge exerts a slight pull on your boat. But if you paddle out into the very center of the lake, you find yourself in a place of perfect equilibrium, where the gentle tug of the distant shores all around you cancels out. Now imagine that one entire half of the lake suddenly and mysteriously drains completely dry. The equilibrium is shattered. You are no longer in the center. You are now right next to a massive, empty basin. The water from the full side of the lake now has a net pull, drawing your boat away from the empty side. From your perspective on the boat, it feels as if the empty side is actively pushing you away. This is the essence of the dipole repeller. It is a cosmic vacuum so profound that the relatively denser regions surrounding it, including our own, experience a net gravitational push away from it. It's not a true anti-gravity force, but a gravitational deficit so extreme it functions as one. The existence of such a repeller solves a long-standing puzzle in the motion of our local universe. The pull from the Shapley supercluster alone was not quite sufficient to account for our observed velocity. The dipole repeller provides the missing kick. The push from behind that, when combined with the pull from the front, perfectly explains our galaxy's journey. This discovery fundamentally changes our understanding of cosmic dynamics. We can no longer view the large-scale flow of galaxies as being governed solely by the attractive power of massive clusters. We must also account for the potent, repulsive power of the great voids. The universe's motion is dictated by a balanced interplay between the mountains of matter and the abysses of nothingness. However, confirming the repeller's existence observationally is a monumental challenge, arguably greater than finding the great attractor was. This region lies quite inconveniently deep within the zone of avoidance, the same obscured band of the Milky Way that once hid the attractor. But this time the problem is even more severe. The great attractor was a concentration of mass, something that eventually emits light we can detect in infrared and radio waves. The dipole repeller is defined by its lack of mass. How do you observe something by its absence? How do you map a whole? Astronomers are employing incredibly subtle techniques, searching for the faintest, most distant galaxies that might be shining through this void. using them to confirm its immense scale and profound emptiness. They are also looking for telltale signs in the peculiar velocities of the few galaxies that do reside on its fringes, watching for the subtle stamp of its repulsive influence. The dipole repeller forces a profound philosophical shift in our cosmic perspective. It elevates the great voids from being passive backdrops to active players in shaping the cosmos. They are not merely empty, they are dynamic agents of motion, their gravitational shadows wielding as much influence over the paths of galaxies as the bright lights of the superclusters. This discovery suggests that to truly understand the architecture of the universe, we must map not only the glittering cities of matter, but also the vast, silent deserts between them. For it is in these deserts that a strange and powerful form of negative gravity holds sway, pushing the universe into its inevitable motions. From the ghostly whispers of missing baryons to the impossible spin of dark filaments, from the chilling cold spot that shouldn't be to the ghost galaxies that defy all logic of survival, our journey through the cosmic web has revealed a universe far stranger and more wondrous than we ever imagined. We've stood before the impossible scale of the Hercules corona Borealis Great Wall, pondered the energetic riddles of cosmic radio bubbles with no clear source, and felt the philosophical disquiet of the axis of evil, which suggests our place in the cosmos might not be so ordinary after all. We've been swept up in the dark flow toward the unseen, grappled with the missing lithium from the universe's first minutes, and detected magnetic fields in the void with no known power source. The plot has only thickened from there. The Hubble tension throws the universe's expansion rate into question. The searing, unexplained heat of the filaments points to a hidden cosmic engine, and the enduring mystery of the great attractor reminds us that colossal forces still hide behind the veil of our own galaxy. We've even dared to entertain the possibility that quantum entanglement might stitch the web together, and that the profound emptiness of the Borealis void might be a statistical impossibility or a window into the multiverse. The discoveries keep coming, the frothy, clumped gas that defies our smoothest simulations, the aligned patterns in the universe's first light that hint at a pre-Big Bang reality, the anomalous elemental abundances that rewrite the story of cosmic forges, and the tantalizing possibility that we live in a local void skewing our entire perspective. We've seen how the distribution of dark matter itself might be wrong, how cosmic rays break the universe's speed limit, and how the very connectivity of the web might bear the fingerprints of quantum gravity. The Etherington tension challenges the constancy of light itself. The precocious early web suggests our cosmic timeline is flawed, and the final revelation of the dipole repeller shows us that emptiness can exert a powerful push, completing our dynamic picture of cosmic motion. What becomes undeniably clear after exploring these 25 enigmas is that the cosmic web is so much more than a simple skeleton of galaxies. It is a dynamic, energetic, and deeply mysterious entity. It is a particle accelerator, a quantum computer, a historical archive, and a cosmic regulator all at once. Each answered question seems to unlock 10 more, revealing that our standard models, while powerful, are merely a first draft in our understanding of the cosmos. The filaments are not just challenging what we know, they are actively guiding us toward what we have yet to discover, perhaps a new understanding of dark matter, a modification to gravity, or a complete revision of our cosmic origins. This isn't a story of failure, but one of thrilling potential. We are living in a golden age of cosmology, where each new telescope and sky survey peels back another layer of this profound mystery. The cosmic web is the universe's greatest structure, and it is also its greatest teacher, patiently revealing the gaps in our knowledge and compelling us to think bigger. Now we want to hear from you. After this journey through the unexplained, which of these phenomena captured your imagination the most? Does the philosophical shock of the axis of evil resonate deepest? Are you more captivated by the impossible spin of the dark filaments or the terrifying scale of the Borealis void? Share your thoughts in the comments below. Let's continue this conversation about the greatest mysteries that bind the cosmos.